So, that box representation you are seeing in k dimension correspond to k interval graphs, right. You are not losing any information, because when you can recreate once a k interval graphs are given, you can recreate such that their intersection happens to be the edge set of one graph. You can in fact draw that graph in k dimension as box, if and only if. It is possible that some of you are a bit confused about whether it is all working out. The people who are more rigorous will be feeling a little uncomfortable about this projection and all, but that is a matter of just working out. Think a little carefully and then you will understand it. So, as of now the take home is only that this geometric question has a somewhat like more or less combinatorial interpretation, namely the equivalent formulation, namely that the minimum dimension in which a given graph can have a box representation, axis parallel box representation, is exactly equal to the minimum k, such that there exists k interval graphs on the same set of vertices, such that the intersection of the edge sets happens to be the original edge set, right. Now, that is all you have to look, right. So, in terms of interval graphs you can argue now for this thing. Now, let me argue that it is not possible to have for this Roberts graph n minus 1 intervals such that the intersection of the edge sets is the edge set of this thing, right. Why is it so? Because the reason is only this thing. So, suppose these are the missing edges, all other edges are present. Now, it is clear that if I take one of the intervals, say whatever interval graph I am getting in the first axis, right, can I have both these edges missing there? That is the question, together simultaneously missing there. Suppose you take one interval graph, because no, it is not possible, because you recall this graph has all these other edges present, right, because all these other 4 edges are present. So, the interval graph has to be a super graph of this because the present edges should be present there also. Suppose these 2 edges are absent, what do you see there on those 4 vertices? It is a C4, right, induced C4, and definitely we know that interval graphs are Gödel graphs and C4 cannot be there. So, therefore, one of these absent edges can be absent in one interval graph. So, not the 2 of them can be absent in one. That means how many interval graphs are required? Yeah, for each one we need a separate one, right. So, if there are 2n vertices, then n missing edges, n absent edges. So, then n things are required, n interval graphs are required. So, dimension should be at least n, right. So, in other words, if you want to formulate it in terms of pigeonhole principle, you just say that suppose it was n minus 1 dimension, then there exists n minus 1 interval graph such that the intersection of the edge sets is the same as this thing, but then there are these n absent edges. So, n minus 1 interval graphs, each of the absent edges should be absent in at least one of them, but then that means by pigeonhole principle that the pigeons are these missing edges here, holes are those interval graphs, 2 pigeons should be in one hole. So, 2 absent edges should go to the same hole. So, which means that on the 4 vertices forming the end points of that, we should have a C4 like this. It is a contradiction. So, therefore, we can always have there exists interval graphs of there exists graphs whose boxicity, the minimum dimension in which you can get a box representation, is at least number of vertices by 2, right. So, here 2n vertices and a number of vertices. You can put floor or something like that. So, there exists one. Now, I will also show that that is the tight one, because you can always, given any graph, you can get an interval representation, say a box representation in that many dimensions. Before that, let us see a very easy way of doing it with in n dimension, because this is one question which usually mathematicians ask when we talk about a new parameter, boxicity, is it well defined? What means given a graph, yeah, can you say you can talk about it, this is the dimension, but is it infinity or something like that, right? Is it finite, right? Is it finite? So then yes, it is always, because for a finite graph you can have, because so it's possible that you can't even have a box representation, then there is no point in asking that what is the minimum dimension in which you can represent it, right? So this is very easy to see. What you do is you take each vertex, corresponding to each vertex you introduce a interval graph. You will have an axis for a vertex somehow. So what do? So suppose V is the vertex, so you put an interval for that V first, this is V, and all the vertices which are supposed to touch it, that means supposed to be neighbors of it in the graph, given graph. So this is n of V, we can put it like this, and all the vertices which are not neighbors of it, non-neighbors of it. So this is V minus V union n of V. Right. This can be collected here, right? You can use the same interval for all of them. Now do it for each vertex separately and put it on different axes. Now you construct the box representation from this by taking the Cartesian product, right? Each vertex will get a box. Now I claim that this is a correct box representation for your given graph. Why is it so? This is because each interval graph I have created is a super graph of the original one, because every edge which is present is still present here, because you see V and this thing all neighbors, these edges from V are present here, and others are all forming a clique here, because the outside vertices, whether it touching B or not, so they are all going through this point, and therefore they are forming a clique. Therefore there is no issue about any edge missing on that part. And with V, whatever edge is to be there, it's there, whatever edge should not be there, it's not there. So therefore all edges are present, all edges present in the graph are present in these interval graphs I created. Now if a particular edge is absent, say that a absent edge may be in, like from V to U edge. So when you created the axis for V, so you know that you have separated it out. Now you have kept it in the third layer, right? V, and then its neighbors, non-neighbors are far, so that there it's separating, right? So therefore this will work out. So it's a picture, when you draw the full picture it may not be very clear to you, but then when you argue like this it should be very clear, right? So actually let me see how much time, 46. Okay, now what I try to do is I will skip the n by 2. I will try to do a proof that if the maximum degree of a graph is delta, right, then we can have a box representation in a space of dimension delta square, sorry 2 delta square. This is what I will do. Okay, quickly. Right, it will only depend on the maximum degree. It says that even if the graph is very big, but if all your degrees are small, you can actually manage to have a box representation in small dimension, right? So for instance, for k regular graphs, only a k square dimension is required. In fact, you can make it even smaller. It is finally order of k log k into something. This what. So actually, log square k was only known till recently, but now in the last month or so, there was a paper which came by removing another log k with little extra, right? So, but that is a bit more complicated, but this is quite easy to understand, right? How do you this is again you will see that though the problem is quite geometric, I mean you do not have to think too much about geometry here, mostly we work with this interval graph model, and that looks completely combinatorial, right. It is a combinatorial thing. So, therefore, it will be very clear. Maybe the geometry is somewhat captured in the geometry inherent in the interval graphs, right, little bit intervals and all, but otherwise it simply disappears. So, though it is when it's box representation, that is quite interesting, that the problem looks geometric, but it is a combinatorial question. So, now how do I do this thing? So, a graph is given G, right. So, instead of showing that 2 delta square is an upper bound, what I am going to do is that 2 into chromatic number of G square is an upper bound is what I am going to do. What is G square? You can see that if I do this thing, this will come, because can you tell what is chromatic number of G square in terms of the maximum degree of G? So, when you take the square of a graph, how does the maximum degree increase? Because a vertex is like this. Oh, okay, what do you mean by square? Square means, yeah, suppose this is there, so you need to add this edge, that is what it means, right. So, take the graph and keep the everything in the graph as such, but then you add a few more edges, which are those edges between pairs of vertices which were at a distance of 2 in the original graph, right, all those edges, right, that is like squaring, that is the squaring. So, a lot more edges will be added now. For instance, if I square this, then I will add this edge, I will add this edge, I will add this edge, like that, right. So, that is squaring. So, now the first question is, if I square a graph, how will the maximum degree go up? How much will be the maximum degree in the new graph? Suppose this is a vertex, this is delta neighbors here. So, it is quite possible that these are all delta minus 1 of them, they are all different, right, suppose in the worst case. Then how many, so when this k will be connected to how many new things? So, for instance, this will be connected to this, right, all of them. So, this, like that. So, connected to how many neighbors will be there then total? So, it should be delta into delta minus 1, right, plus original delta, that many neighbors will be. Delta square minus delta plus delta is equal to delta square. So, that plus delta comes from this original neighbors, right. So, total delta square neighbors can be there, total delta square is neighbors, that means the maximum degree can go up to delta square when you square the graph. So, now do you know that terms of the maximum degree you can get a upper bound for the chromatic number, right, chi of G square is, but here G square's delta is delta square now. So, we can put delta square plus 1, delta square plus 1, right. But you can do a bit of improvement on this thing, because there is something called Bru's theorem, which will allow you to get rid of this one, except for couple of special cases, like there are only 2 cases where, when for connected graph there are only 2 cases where delta plus 1, maximum degree plus 1 colors are required. One is complete graph, right, because n minus 1 is the degree and then colors are required, and the other is odd cycles, namely odd cycles degree is 2, but we need 3 colors, Those are only two cases, otherwise you need only delta. So, you just can take care of this and that will become this thing. And because I am going to prove that boxicity is at most 2 times chi of g square, this will be 2 times delta square. This is what I am going to do, right. And now what do? I square the graph, right. Given the graph G, I square it. First step is square it. Once I square it, then I color it with chi of g square color. This is the next step. Once you color it, you get color classes of g square, right. Each color class is a vertex set only. Now you can take that color, now g square is not required, you can take that color classes and then come to G and identify those color classes like this, say in G. All the edges here are in G only, this is G only, but the color classes of g square, right. So, do you agree with me that a color class of g square will be a color class of G also? Should be, right, because a color class of g square is an independent set there, and in G it should be a color class, because in G if there was an edge there, that will be in g square also, right. So, this is just that in G I could have got a smaller chromatic numbers, some bigger color classes could have existed, but now in g square, because the extra edges are added, there may not be color class, but whatever is a color class in g square is a color class in G also, right. Now what I am going to do is, corresponding to each color class of G, let us call it C1, C2, C3, Cg square, C chi of g square. So, maybe CH or something like that we can call. I will introduce a new graph. My intention is to introduce a new graph corresponding to each of the color class. So, this is the way. For C1, how will I do? So, suppose this is C1, so the vertices of C1 will be here. Now, I collect all the other classes here, C2, C3, C4 and CK, so CH, all of them, and then what I do is I make it a complete graph. That means, if at all some edges are missing there, I will add them. So, some between the color classes, so within the color class there was no edges, but I fill all of them and then put all missing edges and make this a complete graph. And then here between this and this there were some edges in G, remember, not in G square, in G, those edges are kept as such, and this is an independent set, you know, right. Yes, it is. So, let us call this graph H1, right. Now, how many such graphs are created? For C1 you created one like this, and similarly for C2 you can do the same thing, but here now C1, C3, CK will be there, and this will be complete graph, and these edges will be as in G, and this will be an independent set. This will be H2, right. Like that, how many graphs will be created? H1, H2, H equal to chi of g square, right. So many classes. Now, my claim is that my original graph G is equal to the intersection of these graphs, equal to 1 to H. If I intersection means it is on the same set of vertices. So, intersection means intersection of the edge sets. If I take the intersection of the edge sets of all these graphs, I will get back G. Do you agree with me? First, see, it is very easy to see whether it is intersection or not. What you have to only check two conditions. One is whether the claimed these graphs are super graphs of the original graph. All the edges of the original graphs are present there or not. Yes, it is present, because we only added edges there, right, to create HIs. So, therefore, they are super graphs. And now, the crucial thing to verify is, if a particular edge was absent in the original graph, it should be absent in one of these things, at least one of these things. so that when you take the intersection, that edge disappears, right? Because in the intersection only things which are there everywhere will come, right? So, if a particular edge is missing in any of these things, when you take the intersection, that will disappear. So, we have to make sure that if all true that all of these things are super graphs of the original graph, but we have to also make sure that if a particular any edge is absent in the original graph, uv is absent in the original graph. So, uv is not there in the edge set of G, then we have to show that there exists an I such that uv is not an edge of E of Hi also, right? There exists one of these graphs there. Is it true? Now, you look at where U and V are there together. Suppose if both of them together appear in one of the color classes of G square, then we are done, right? Because anyway, when I construct the graph corresponding to that color class, then anyway in that color class I haven't filled any edge. That was independent set. The only issue is when this edge U and V was across two color classes. U was in some Ci and V was in Cj. Now, you can take any one of those. There are two possibilities now we can consider: the graph corresponding to that color class Ci or the graph corresponding to the color class Cj. Any one will work for us. So, take the graph corresponding to the Ci. U is identified here and the remaining things are here. So, click, and somewhere here we have your Cj and your V is here, right? And this was missing edge. So, now in this graph will we have this edge? No, because the connection between this and this was as in G, right? And we haven't added anything across, right? It was something, some edges are there, but those edges were there if they were there in G. But now I know that between U and V there was no edge in G. So, therefore, I will not have this edge here also, right. So, that UV edge which is missing here, right. So, my claim is that if an edge UV is absent in one of those HIs, then it will be absent, in G, it will be absent in one of the HIs, and when you take the intersections, that edge will anyway disappear. So, therefore, what you get back then is the edges which are present in G, namely G, right. Therefore, intersection of HIs will be equal to G. This is what we get. So, does it mean that boxicity, see I equal to 1 to H here, does it mean that boxicity of G is equal to H just because you showed that intersection of this thing is H? Not necessarily, because HIs are not interval graphs. Because if each HI was an interval graph, then we are done, right. If each HI was an interval graph, then it was done, but it is not true, because this is actually a split graph, if you note, right. Yesterday I introduced the split graph. So, this is a clique and there are these edges between them. This is an independent set. One side we have an independent set, the other side there is a clique, the edges are going across. This is a split graph, not an interval. Split graph is a chordal graph, but not an interval graph. We are still not there with the interval graphs. So, then how will I manage? I can manage with 2 factor now. That means, for each of these HIs, I can get 2 intervals. Suppose given an HI, I will be able to find 2 interval graphs II1 and II2 such that their intersection equal to this HI. That means, these are boxicity 2 graphs. Each HI is a boxicity 2 graph. That is what I will call. Though they are not interval graph, they are boxicity 2 graphs. When I take the, then I will be able to find out. I will be able to find out 2 interval graphs such that they intersect, which will finally prove that 2 into H is equal to 2 into chi of G square is the boxicity of the graph. Because if I take this thing, intersection of all these things together, right, so II1 plus II2 plus, right, into every those 2H intersection of 2H interval graphs will form the original graph. So, how do I do that? So, now look at the picture of the graph once again. So, there are some edges here, some edges here, not so thick maybe. So I can number this as 1, 2, 3, some t, right? These are remaining things 1, 2, 3 to n dash being n minus t, right? Now, though it will look like how is it possible, I am not going to claim that all split graphs are boxicity 2 graphs or something. It is not true also. In fact, there are some split graphs which have very high boxicity, but this particular split graph is like that. So, from one look it is not visible, but in the second look we will see that there is some structure there. What is the structure? For instance, if I look at this graph and then I take a vertex from this part, any vertex from this part, say. So, any vertex from this part. So, is it possible to have more than one edge from this vertex into this set? That is the question. More than one vertex. For instance, if this is u, can I find x here? Can I find y here such that u is connected to x also, y also, maybe more things. So, at least 2. Can you find that? That is the question. There is a reason why you cannot find. So, given any vertex on the clique side, it cannot have more than one neighbor in the independent set side. There is one simple reason why this is true. That is the only crucial observation here. What is that? Can anybody guess it? Because we have to recall the way in which we came. We know how did we make these color classes? We went to G square and made the color classes. There should be some reason for that. Now till now I haven't used it, right? What was the reason for going to the square of the graph and make the color classes? Yes. Then you have this edge, right? Because in because this edge and this edge is there in G. So then x and y were at a distance of 2 in G, right? Then this edge should have come. So then, but then this would not have become a color class in G, right? So the same color means x and y were not having an edge in G square means, so two edges cannot be there like this, because between x and y this path would have existed in G itself. So this edge would have come, right? So that is the reason, right? That was with a good planning, we had taken that G square and took its color classes, foreseeing this situation, right? So that otherwise there was no reason to go to the G square. You could have taken some color class and started working. No, it will not work that way. So therefore, so what happens is, okay, in this case, so this is the clique, and so here each vertex here can have only one neighbor here like this, only one neighbor. From here you can see many, probably that is not blocked. This is possible, this is quite possible, but not the other way. From looking from here you will see only one. Looking from the clique side you will see only one neighbor in the independent set. From the independent set side you may see many in the clique, right? So it can be several stars like this. Now this helps us to prove that the boxicity of this graph, namely an HI, is 2. Is 2 or at most 2. Why? Because I can construct two interval graph now, such that the intersection of this thing is this thing. What I do is, for that color class, so that means the vertices here, so let me call it 1, 2, 3 up to T. Then I will put small intervals in that order, say 1, 2, 3 T, 1, 2, 3, 4, 5, so T, like this, right? And then this is, before this I can start somewhere here everything else, every other thing on the clique side I can start, interval can start somewhere here, so that they form a clique. Everything starts here, therefore they will be intersecting here and they will be forming a clique. and up to where should I take it to? So, of course, that is dictated by the neighborhood, right. So, because each vertex here, suppose I take an x vertex here, it will see one neighbor here, say 4 is a neighbor of x, only one neighbor. So, you have to go there and touch it. It has to go there and touch it. No need to go beyond that, but it has to go all the way to touch it. And for everything, so you have a y here, so you may be going up to 2 and you have a z here, it may be going and touching, say its neighbor, say some I or something like that. So, exactly to where it should go, because there is one single neighbor which is seeing in that 1 to t, right, it will go and touch it. Now, what it has done is, each x is seeing not only its neighbor, but also all the neighbors which are numbered below, all the vertices of that independent set which are numbered smaller than that, right, 1 to 2, 1, 2, 3 up to its neighbors number, right. That is what is happening. That is not what we want only that. Tell me what should I do now, because I am going to make another interval graph. So, you understood my situation, right. So, I want each vertex from here, the clique side should see exactly its neighbor, one neighbor only is there from the independent set. So, the idea was to put the independent set vertices like this, and the clique vertices will come from one side and catch its neighbor. But then when you catch it from this side, what happened is it caught more than what it can, because anyway it has to go through, right. So, whatever was in between was caught, and definitely we want to somehow get rid of them. The thing is, now this time you should start from the other side. Now, here we started from this side, now this time I should start from this side and come and catch whatever I should catch. Now, this portion I was getting unnecessarily earlier, now that is left out and I will get this portion unnecessarily, but then that was not there in the earlier, right. Okay, more clearly, suppose this was my t things and something is coming and this was my aim, it was my, so I caught these guys unwanted last time, but now the next time I am coming from here and catching the same thing. So, I am catching this unnecessarily, but these are all released now, right, this is released. So, but in the earlier one this was not there. So, together they are only seeing in the intersection they are only seeing this one guy, right. So, that is, so look from here and look from there. So, you got rid of all the unwanted things, right, you got only this. So, therefore, this two interval graphs, this will happen simultaneously, for every vertex is doing its work, right. In 2 chances he gets, he comes and catches from this side and this side. So, all the unwanted things will be removed. It is like a small puzzle which you can ask people, right. So, therefore, we get in 2 interval graphs we get, so that means you can find I1 intersection I2 is equal to Hi, right. So, finally, what we get is G is equal to H1 intersection H2 intersection, say this one, pi of G square, and here this is equal to I11 intersection I12 intersection I21 intersection I22 intersection. So, this is we have, which means boxicity of G is less than equal to, right, 2 times chi of G square. Okay. And from this thing we got, with a little help from Bru's theorem, we will get 2 into delta square, right. Chi of G square, because G square's maximum degree is delta square, we could have got 2 into delta square plus 2 very easily, because delta square plus 1 was an obvious upper bound for chromatic number, but with a little help from Bru's theorem we get rid of that extra 2 and then you get 2 delta square, right. This is the complete proof of that. So, it is 13:15, I think it is my correct time. So, there are many things about these things. I just wanted to give you an introduction of this stuff. So, I do not know whether it was I hope you understood what we told, a simple thing, a little cleverness, that is all, here and there. right. But there are many the things is the nature of most of the proofs will be like this, a little trick. That is what we will need in most of these things. Though the geometry is usually a little clumsy to work with. Luckily here we don't have geometry. The geometry is in the results. Proofs are mostly combinatorial. The result will be geometric. You can always see a geometric interpretation of that result, which is quite intersection graph of boxes in some dimension. But all the proofs will come in combinatorial things, though we don't have the feel of how the geometric thing, it's in proof step by step how the geometry is moving, but the analysis is very easy. It's very pleasant combinatorics. That is the thing. So therefore, that's a mix of combinatorics and geometry. In results geometry, but proof combinatorics.